All right. Did the recording start?
We got you.
Okay. Okay. All right. So hello everyone. This is the second SWE session, and we'll be covering dynamic programming today. I think there may have been some mix-up that we may have been doing backtracking. It turns out we'll be doing backtracking a different week. So sorry if you were expecting that and are now disappointed. Come for backtracking when we do it. And so today we'll be covering dynamic programming, and this is like what the agenda will look like. So we're going to discuss what specifically dynamic programming is, and then once we kind of get through some of the big ideas, we'll go into some practice problems to help kind of convey the structure of a dynamic programming problem, and then we'll just end with some final thoughts about it and close off. So before we start, I do want to mention that there's expectation that we're like familiar with recursive problems and solving recursive, any sort of algorithm that requires a recursive solution. And the reason that is because dynamic programming is like super tied to recursion, and so having some intuition about recursion helps a lot with dynamic programming. And so I think this is also specifically for people that have not taken CS 330 yet. So in CS 330, you formally go over dynamic programming, but it seems kind of unjust that you have to take that class to learn what dynamic programming is. So hopefully what we cover here today will be enough for you. Yeah, so let's get right into it then. So what is dynamic programming? So it is technically an optimization technique which uses solutions to smaller subproblems to build towards the end solution. And so this doesn't really mean that much for us, especially when we're trying to think about how we might code a dynamic programming problem or solution. But the word that I really want to point out here is the word subproblems. And this word is going to come up more throughout this session, and to just kind of keep that word in the back of your head. And at the beginning it might not make that much sense, but as we build through like some of the ideas and examples, it'll start to demystify itself. So subproblems. Okay, so now to frame dynamic programming with respect to recursion, I'm going to say that the top-down approach to a problem might come as a recursion technique. And then dynamic programming is going to be a bottom-up approach. So I think like if you were to look this up, there might be some confusion between what is top-down, what is bottom-up. Is recursion only top-down? Is dynamic programming only bottom-up? And for the sake of this session, I'm going to say that bottom-up and dynamic programming is separate from top-down and recursion. Okay, and I guess I'll explain a little bit more why I'm making that distinction in a bit. Right, so we have this kind of dichotomy between recursion and dynamic programming, where we can start with like the main goal, and then with recursion, we will make a bunch of recursive calls that eventually kind of fall down and then reach some sort of base case. And then after that, we can start finally giving out answers, right? Whereas for the bottom-up approach, we'll start with a base case, and then we'll build up towards the end solution, right? So it's kind of this like mirrored view, right? So the first thing I want to mention something about recursion, right? So this might be some recursion tree, right? You might see a recursion tree like this, right? Where f of n is some function with input n, and to compute f of n, we need to compute f of n minus 1 and f of n minus 2, right? And you might notice that, okay, there are a lot of function calls that repeat themselves, right? We see f of n minus 2 come up here twice, and then we see f of n minus 3 also, and f of n minus 4, right? And if we kept going, we would see a lot more of those as well, right? And maybe even more so is that we see a bunch of f of 1s, right, which would be our base case. And so you might say, okay, why would I want to recompute something that I've already computed before, right? And so this is the process called memoization. So I did spell this correctly. It is not memorization, it is memoization. And this is the process by which we save results from a function call and then access those saved results instead of recomputing the function, right? So you can think of this kind of as like caching answers to problems, or like saving the answers to problems in an array and then accessing that array instead of recomputing the function, right? And so the reason why I grayed out all of these function calls here is because with memoization, we'll never end up making those calls, right? But yeah, so what's left is just these this bolded line down here that goes on the left-hand side. So you might say, okay, if I can compute f of n just by computing f of n minus 1 to all the way down to f of 1, why can't I start at f of 1 and then go up to f of n? And this is the idea of bottom-up. This is the idea of the bottom-up approach with dynamic programming, right? So dynamic programming will say, okay, start at f of 1. And then with the information from f of 1, we can compute f of 2, and then f of 3, and then we can go all the way up to f of n, right? And so this kind of way of computing the solution is very linear, and it's like is perfect for an array structure, right? So these are all kind of like tidbits about dynamic programming, right? So I kind of mentioned that dynamic programming and recursion are very closely related, right? So you may say, okay, if I can solve something using recursion, why would I need to learn this dynamic programming to solve this problem in a different way, right? And there are actually many reasons, right? So the first reason is that iterative solutions are often easier to write than recursive solutions, right? So recursive problems, although they might be shorter, sometimes they require a lot more brain power to get this one line of code out, right? And oftentimes I hear this phrase where you like get lost in the recursion because you kind of start making these recursive calls and then soon you don't know where you are because you're trying to keep track of a bunch of different things, right? But if everything is iterative, then you just have some for loops and you pretty much know where you are whenever you're writing code. The second thing is that with recursive solutions, it's sometimes really difficult to analyze the complexity of it, especially when we throw in memoization, where now we're not really sure, you know, how many layers of the recursion we need to go through, or how often we can access the memoized array, right? So we either need some intuition about how to calculate the runtime for a recursive solution, or we have to explicitly solve like a recurrence relation, like T of n. If you remember in 201, we did a lot of T of n stuff. And then on top of that, function calls take up memory space on the stack, right? So you need to factor in memory whenever you write a recursive solution, right? And this all leads to the fact that dynamic programming solutions and bottom-up approach solutions are significantly easier to analyze, and we'll see that firsthand today. And then the last point is just that sometimes if we frame a problem in the scope of dynamic programming, it's easier to solve than using a recursive solution, right? So with all that truth about dynamic programming, I do want to make this statement, which is, so if the gray part of the screen is all the problems that can be solved using recursion, this white circle is all the problems that can be solved using dynamic programming, right? So all dynamic programming problems can be solved using recursion, but it's not necessarily true the other way around. And this is because dynamic programming takes advantage of a very particular structure from the problem and exploits that to improve the runtime or improve the space of the algorithm, right? So we'll just keep that in mind. And so throughout, like as we go over these problems, oftentimes you'll be seeing like, you'll kind of be reminded of so like some sort of recursive function or like a like recursive type of call. And that should make sense because dynamic programming and recursion are tied together, right? So does anyone have any questions about dynamic programming at a high level? And you can also feel free to like type in the chat. Alrighty. So with that, I guess we'll go into our first practice problem, which will be counting steps, right? So given some staircase of size n, how many ways can you reach the top of the staircase, given that you can either climb 1 or 2 steps at a time, right? So just to kind of go back to the fact that this is like an interview prep course, like one thing that you should do whenever you see a problem is try to like come up with possible questions that will help clarify some of the information about the problem, right? So does anyone have any clarifying questions about the problem statement?
What is, I guess, like valid inputs of n? Like, would we ever get like 0 or negative values?
Yeah, that's a great question, Will. And yeah, so the answer will be n will always be positive integer. Yeah, so that's actually a really good question, and that leads us into just this slide, which is here are some of the things you might want to ask about, right? So yeah, so the input is strictly positive, and the second bullet is that we want the number of ways to reach the final step, right? So we don't want to go past the final step, we just want to reach the final step. So the way you can think about this is that maybe we're on an infinite staircase, and the question is, okay, what are the number of distinct ways to reach the nth step in this infinite staircase, right? And we do want the number of distinct ways, so we can't just like calculate some giant number and give it, return that. Yeah. Any other questions about the problem? Guys, just feel free to interrupt me as we go. But so this problem is, it's not super complex. It's a fairly simple problem statement. And so we can try to like build straight towards a solution right away, right? So the first thing that we'll notice is a pretty simple observation, which you should try to get in the habit of making, right? Which is, okay, what if the input is size 1, right? What is the answer? So the number of distinct ways to reach the first step is going to be 1, right? Because we can only take 1 step. And then since we made this observation, we might as well make the next one, which is, okay, what are the number of distinct ways to reach the second step? And that's going to be 2, right? Because we can either take 1 step twice, or we can take 1 single 2 step, right? So that's kind of, those are the first 2 observations that we might make. And then the next one is, okay, so say we're at some random step I, okay? Since we can only take 1 step or 2 steps at a time, the next place we can go is either I plus 1 or I plus 2, right? And then if we kind of flip that around, okay, so say we're at step I, then we had to have come from either step I minus 2 or I minus 1, right? And that's going to be our final observation, right? Which is to reach step I, we must have been either at step I minus 1 or I minus 2, okay? And this kind of leads into a very like recursive structure where we had to have like been somewhere before to reach where we are now, right? And so, yeah, so now we can actually start going directly into a pseudocode solution. And so the first thing that we'll do is we'll initialize this array, okay? And this array will be, so AI will be the number of distinct ways to reach the ith step, right? And so if we have the fact that to reach step I, we must have been either at step I minus 1 or I minus 2, right? The number of distinct ways to reach step I is going to be equal to the number of distinct ways to reach step I minus 1 plus the number of distinct ways to reach step I minus 2, right? So that kind of leads us into the next part, which is, so first, and then we have our base cases here. And then for I equals 3 to n, we'll compute this value, right? A of I is equal to A of I minus 1 plus A of I minus 2. And then the last thing we can do is just return this solution, right? A of n, which is the number of distinct ways to reach the nth step, okay? Does anyone have any like confusions or questions about this pseudocode solution? Cool. Okay. So this is what the code might look like. So we'll have this base case at the very beginning, and then we'll initialize our array, and then we'll fill in the first two entries. And so notice here that I'm electing to leave the A of 0 alone because it's easier to write like this. But yeah, there are many ways you can write this. And then I have this for loop here, which does this computation that we've had here, right? So this is actually very easy to analyze, right? Because we just have a single array of size n plus 1, right? So the space is easy. And then we only have a single for loop. So the runtime is also easy to analyze as well, right? And they're both linear with respect to the input size, right? So let me make a couple comments about this. So specifically, I do want to point out again this kind of formulation that we have here, where A of I is equal to some function of the previous subproblems, right? So we can think of A of I minus 1 as a subproblem, right? A of I minus 2 as a subproblem. And with the understanding that we've correctly computed these two, right, we can compute the current solution. And then we can build up towards our end goal at the very end, right? So does anyone actually have any comments about this solution? Whether this reminds them of something, or there's some way we can improve the efficiency of this algorithm?
Well, I think you only need the previous two values. So you could just have two variables to store basically I minus 1 and I minus 2.
Yeah, exactly. Perfect, right? Yeah, so we can just keep, just like Rami said, we can just store two temporary variables and then just update them accordingly as we go, right? And so sometimes you'll see this type of dynamic programming problem where we can actually get away with constant space just by keeping a few a few variables and update those variables accordingly, right? And so maybe you've noticed, but this is actually going to be, this problem is equivalent to the nth Fibonacci number. But to be honest, climbing stairs is cooler than the nth Fibonacci number. So, yep. Any questions about this problem? Cool. All right. So now we'll get into our next slightly more complicated example, which is going to be the longest increasing subsequence. And so I do want to say, before I continue, that I've chosen these three problems specifically because oftentimes when you read about dynamic programming, usually you will see one of these three problems come up as an example. So I figured I'll get them out of the way as well. Yeah, so the problem goes as follows. So given an array of integers of length n, find the length of the longest increasing subsequence, right? So any clarification questions about this problem?
If two numbers are the same, is that increasing?
Yeah, that's a good question. So we're going to say that the subsequence has to be strictly increasing. Yeah, and maybe another more general question you might have is, what is a subsequence of an array? And so we'll answer that with an example, right? So let's say the input array is the top one, right? And then the second array is going to be an example of a subsequence, right? So a subsequence is just a subset of an array that keeps the relative order of the elements, right? So we have 10, 2, 5, and 18, all elements of the original array, and they're all in the same order, right? The original order, 10, 2, 5, 18. And then the last example I have here is an increasing subsequence, right? So it goes 2, 5, 7, 18. And yeah, so note that I did not include another 7 here since that would make it non-decreasing, but we want an increasing one. And the reason why I bolded this one is because this is actually going to be one of the longest increasing subsequences, right? So it doesn't have to be unique, right? Because we could have done 2, 3, 7, and 18 instead. But there is only one like longest length, right? And another note that I want to make is that the longest increasing subsequence does not have to end at the last element, right? Let's say if instead of 7 over here we had 100, then we could have easily put in 100 here and then just removed the 18 and had something of equal size, right? So at first this problem is actually seems pretty difficult to solve, but we'll like really look at this example, and then I think the solution will start to show itself. Right, so up top I have the example again, and let's just consider the first half of this array, right? So the first 4 elements, 10, 9, 2, 5, okay? And if we just solve the problem on this half, right, we'll notice that the longest increasing subsequence is 2, 5, right? And if we recall the solution to the whole problem, right, we'll see that 2, 5, 7, 18 is the longest increasing subsequence for the original array, and 2, 5 is a part of that, right? So we kind of notice that, you know, increasing subsequences are made up of smaller increasing subsequences, right? And it already is starting to exhibit this kind of recursive feel where, okay, maybe if we know something about increasing subsequences from previous elements, then we can kind of solve this problem, right? So with that, we'll like kind of go towards, we'll start making some steps to the solution, right? So yeah, so the first thing is what I just mentioned, which is a longest increasing subsequence is made up of smaller increasing subsequences, right? And so basically this is kind of relating a solution to some subproblems, right? And then the next thing is that the longest increasing subsequence could end anywhere, right? So we need to keep this in mind as we write our solution, that it doesn't have to end at the very last element, right? And then the next thing is that if we wanted to add an element to an increasing subsequence, we only need to know the last element that was a part of that subsequence, right? Because all the elements that are before it have to have been less than that one. So we only care about the last element in an increasing subsequence, right? And to kind of push this further, right? If we're adding an element to an increasing subsequence, we don't really care about what comes after, right? We're just trying to add an element to an increasing subsequence, okay? So this would kind of lead us towards a solution, and I'll actually like open the floor if anyone has any ideas about what we might want to do with this, or maybe how we might want to like relate the solution to some subproblems. And yeah, that's all right if you also don't have any ideas or don't want to talk online. But yeah, so basically we're going to kind of go through a similar approach to what we did last time with the counting steps problem. And that's going to be, we're going to construct this array that's going to help us define the problem, right? So we'll construct this array DP, where dpi is the longest increasing subsequence, which ends at the ith element, right? And so with this information, like where would the solution might be? Like where's the solution if we have, like, say we have this DP array that's like filled in for us. So how do we compute the solution for this? Like given all this information.
It would be whatever is in the last index of the array.
So actually, so in this case, since I mentioned before that the longest increasing subsequence could end anywhere, right? It might not necessarily end at the ith element, or I mean at the end of the array, or at the end of this DP array, right? It might be like it might end at the beginning or something. Did that make sense?
Yeah, okay, so then would it just be the biggest one in there?
Yeah, exactly. Yeah, so we'll take the max over all the elements in this array, and then that'll be the answer, right? And notice here that, like, say we're trying to figure out what DPI is, we actually don't really care what happens after, right? And so now the real question is, how do we compute DPI? Does anyone have any like thoughts or ideas about this? And this is like under the assumption that we've already computed everything before DPI. Okay, so we've computed like DP1 to DPI minus 1.
I would say like start looking, like you said, on the elements from the left, and if I, like the value at I is greater than like some other index on the left, then you can like assume you can just add it to the subsequence. So you would add DPI or DPI minus like X or something to +1, and that would be DPI. And so you could take like the highest previous subsequence that you've seen and build off of it. And like you would build off of it as long as it's legal. So as long as like I is greater than.
Yeah, exactly. Yeah, that's pretty much exactly what we're gonna do. And notice that Will was pretty much talking about how we're relating DPI to all the previous subproblems, right? And that's really the key with dynamic programming. Okay, so the pseudocode solution is going to follow a similar structure to what we've seen before. So we'll start with the initialization, then we'll go through a for loop and compute DPI, and DPI is going to equal 1 plus the longest increasing subsequence so far, where we can append the ith element to it, right? So this is like another way to say what Will had just said. And then what we return is we return the max over the DP array, right? And so let's take a look at what the code is. So here we have the initialization piece, and we just keep a variable that will run over, that'll just keep a track of the longest increasing subsequence so far. Then we have this for loop here. And then here is going to be DPI equals 1. And what this line is saying is that, okay, if all else fails, we can always just start a new increasing subsequence at this element, right? To say like the smallest element of the array is like halfway into the array, then we have no choice but to start at start a new increasing subsequence there, right? And then this is a logic that Will was saying exactly, right? So we'll loop from 0 to I minus 1, and then we'll check if it's valid. And if it's valid, we'll just compute the max between the current solution and j plus 1, right? And then we'll just keep, we'll just update our overall if necessary, and then return it at the end, right? So again, the runtime is pretty simple to analyze, right? So the space is linear, right? Since we just have a single array. And then we have 2 for loops. And if you're not very familiar with this structure, where we iterate from like 0 to n and then 0 to I, this always ends up being n squared. There's like a geometric series argument for that, or like geometric sum for that, yeah. So this is an example of a one-dimensional dynamic programming table, where our DP array is one-dimensional. So last time we were able to kind of cut down on the space, but here we cannot because we have to look at everything before, right? I think there is a better solution to this that uses like a binary search function, but I think it requires a little bit of like a mind stretch. So I don't know if I would expect that like while you're doing an interview or something. But yeah. So any questions about this solution? All right. So the next and final problem is going to be the famous change making or coin change problem. And so maybe you've seen like some variation of this in the past, but or maybe you haven't. But I think this is a pretty popular problem to go to for dynamic programming. And I was actually given this interview question at like some company that I interviewed at. So it does come up sometimes. And so the problem is, given n coins, which are the denominations, right, and some amount, you want to find the least number of coins required to make that amount, right? And sometimes it's not possible. So in that case, return -1, right? Yeah, on LeetCode, it's called coin change. If you want to like take a look at that as well. Right. So let's. Does anyone have any questions about the problem statement? Yeah, I think this one's pretty clear. You might have some questions on the denominations, but I think generally this one is pretty clear. So let's just look at an example, right? So given 1, 5, 10, 25, 50, and amount 99, right, the goal is to figure out the least number of coins. Does anyone know the answer off the top of their head? I guess this is not really the point of, yeah, it's going to be 8, yeah. Yeah, so 50, 25, 10, 10, 1, 1, 1, 1, 99. And so these, actually, I will make a note that these denominations are unique in the sense that we can actually, with these denominations, we can solve this problem greedily and just take as many of the biggest coin as we can. But that's actually not always the case. And if you don't believe me, like try different denominations and then see that, oh, it turns out you can't always just take the biggest coin, right? So this is a unique case. I just pulled this one because these are the coins that are used in the US, I guess. Yeah, so basically the solution to this problem comes from looking at how we got to 99, right? Or how we got to our solution at the end, right? So we have this amount 99, and then we have a bunch of these possible denominations, right? And basically to reach 99, we would have had to add some coin, right? And so we would have had to add some coin to some value, some previous value, right? So I have 5 lines here, and could anyone guess what the number is like underneath each line will be? You don't have to tell me what the number exactly is, but
like 99 minus 50, 99 minus 25, 10, 5, 1.
Yeah, exactly.
So you have 5 ways to get there.
Yeah, exactly. Right. We have 5 denominations, and there are 5 ways we can get to 99. Right. I think I went the other direction, but yeah, same idea, right? And this like pretty much just puts the relation of like a problem to its subproblems like directly in our face, right? There's like no denying that to reach 99 from 98, we can add a coin. To reach 94 to 99, we can add a 5-cent coin, right, etc. And so this kind of really just like tells us like how we might want to go about solving this problem, right? So with that, we can actually try to jump right into a possible pseudocode solution. So if anyone has like some ideas or like how our initialization step might look like, or like what we want to keep track of while we're doing this problem, like, please share. Yeah, actually, I guess we'll just go right into the solution. So the first step is going to be the initialization piece. And we saw before that the way we computed 99 was from previous values, right? So with that in mind, we can initialize an array equivalent to the amount plus 1, right? And each value of this DP array will be the minimum number of coins it takes to create this amount, right? And so with that in mind, like the answer to the problem becomes a little bit more clear, right? And it's also actually very easy to relate this problem back to the previous subproblems, right? Because now with knowledge of the minimum number of coins to make any amount below the current amount, we can just look at those 5 values and then just take the minimum one, right? So for I to amount, I equals 1 to amount, we'll compute DPI. And then so this is like kind of a bunch, but for each denomination, right? So loop over the denominations and then check DPI minus denominations, right? And if that can be made, right, then you just set DPI equal to the max of all of those plus 1. I think I forgot a plus 1 here, but yeah.
Shouldn't it be the minimum?
Yeah, you're right. It should be the minimum. Sorry about that. Yeah, it should be the minimum over all of those. Yeah, nice catch. And then at the very end, we can return just DP amount as a solution, right? So with this pseudocode in mind, does anyone want to have a crack at the runtime and space complexity? We have like another 5 seconds.
It has to scale with both the number of given coins and the amount, right?
Yeah, exactly. Yeah, so the space is the easiest one to do, right? That's just going to be linear with respect to the amount that we got. And then we have 2 for loops, right? One for loop which loops over the amount, and then one for loop which loops over the denominations. So our runtime will be the amount times the number of denominations we have. And so I'm going to like very briefly gloss over what the actual code solution is. And the reason I'm doing that is because like we've essentially solved the DP part of this problem already, but there are a lot of like minor edge cases / tricks that you need to go through to really figure out like the code for this problem, right? So the pseudocode only gets us halfway there, but I think this problem in itself is a good exercise for you to like practice like these little algorithmic like coding things, right? So yeah, runtime s times n, where s is the amount, n is the number of denominations, and space is just O of s, where s is the amount, right? And there's a solution if you like coded it and want to check later, right? So that's really like will be the end of those like our practice problems. These are a bunch of other DP problems that are like pretty common. Some of these are actually like pretty difficult. So the ones we looked at today were rather were pretty simple and compared to some of these. And so definitely like take your time with these problems. And I guess like if DP is still kind of shaky, of course, practice makes perfect, especially for this. And sometimes it's easier to figure out the recursive part. And then whenever you figure that out, always try to go back and maybe see what the dynamic programming bottom-up approach might be. And yeah, so one other thing I want to mention is that so in these three problems we saw, one of them was constant space and the other two were linear. We could also have two-dimensional DP tables. I think you can solve the coin change problem using 2 dimensions if you wanted to. But yeah, and like the ultimate upshot of dynamic programming is that it's super, super easy to analyze compared to recursion. So whenever you get the chance, I always recommend like dynamic programming will oftentimes be easier to analyze and faster to code than a recursive one. Yeah, so that'll be it for today. Thank you, everyone. I'll like send a Google form for feedback because I'm like curious what you guys think and everything. So I've like pasted it in the chat. If you like fill that out like today, right now, or whenever, please do so. And yeah, I think I can stop recording.
Thanks, Dorian.
Oh yeah.
Thank you, Dorian.
Thank you, Dorian.
Yeah.